Yeah, the attendance is a bit thinner than usual, but I will start anyway. So maybe it's recorded. So maybe. Okay, in the agenda that I sent out today, I said that I would the order. I mean, I would first discuss some implementation notes and then finish up the loop invariant discussion. So I will do it in the reverse order. First, I'll finish up loop invariant since I started with motivating it and introducing it, and then I'll first finish that thing up and then get to talking a little bit about the various different ways in which bounded model checking can be implemented for software and why the implementation using SSE notation is more efficient and it's more popular used. So let me start with this. Here we yeah, this is where I was. I kind of made some modifications. Okay, so what is an inductive loop invariant? We saw what an invariant is. Okay, invariant is something that is true invariant for a program is something that you attach at a particular location, and it is true when on every execution whenever the control reaches that particular location. Now here, this is a special kind of invariant for programs called inductive or loop invariant. So in general, a predicate denoting a condition described by a formula, say Li, that is attached at a particular point inside a loop is said to be inductive if it is true for all iterations. For all iterations of the execution of the body. That is, if I start from a state in which the loop invariant is true, and I enter the loop body, which means the loop condition, entry condition is true, and after executing the body, Li must stay true in the state that results after the execution of the body. This is what any predicate that satisfies this with respect to the loop body is called is said to be inductive for that loop. Now, an inductive predicate Li is said to be invariant, that is, it's not inductive or invariant, if it also satisfies the initiation condition. I call it entry check in the the slide that I used yesterday. Sometimes it's also called initiation condition. That is, the first time you enter the loop, that the loop, the predicate Li has to be true. That is, you start from the beginning of the program, and then you execute with whatever precondition that is associated with the entry point, and you execute the fragment of code prior to the loop, then then the loop invariant has to be true upon the first entry. Okay. Yeah, with these two things, then you're guaranteed. If it's inductive and it satisfies the initiation condition, then it is guaranteed to be an invariant as well, because it's inductive, it is true every time you go around the loop, and it is true the first time is guaranteed by the initiation condition. So these two conditions guarantee that every time you are at that point in the loop where which is associated with Li is the predicate is guaranteed to be true. And then
why would you say preloop code? I thought it should be the same as the body, right?
No. Okay, so let me see. So no, the first time, okay, you don't have, if it is true, the first time that you enter starting from the entry point to the entire program, okay? You know, for example, here I do have an example. No. For example, here, so anyway, you see, even of X, what the inductiveness says is, if it is already true at that point, then when I execute the body one more time, then it continues to hold. But what is to say that when you enter this point, the first time from the entry point of the program, that it is true? There's no, because the inductiveness condition itself makes no claim about that Li, which in this case is even if X, is true when you enter it the first time. And that's what the initiation condition guarantees.
So the loop invariant should be true right from the first loop, is it? Right before the first loop.
The first time you enter that point in the loop.
Yeah, at that point, the loop invariant should hold, is it?
That is what the initiation condition guarantees.
I see.
Requires. So it's only when it is inductive, which guarantees that every time you go around the loop, if it is true at that point, then it will continue to be true. But what is to say that it is true the first time you come? The first time you come, it may not be true. For example, if you start with an arbitrary state, here X happens to be initialized to 0. Therefore, the first time you come, even if X is true. But suppose I start with an arbitrary state, okay, in which X could take any value. Then, although even if X is inductive, because if you assume that at that point X is even, then after you execute the body, X plus 2 is, it still remains even. But the first time you come, at that point, even is not true. Okay, X is not even, right? So you do need this condition as well to ensure that in every execution of this program, starting from the entry point, that it is an invariant, that even if X will be true. Okay, with these two conditions together will guarantee that the first time you get to this location from the entry point, even is true. That is guaranteed by initiation condition. And the inductiveness property of this predicate ensures that no matter how many times you go around the loop, that and you come back to visit this location, which is the head of the loop, that Li, which in this case is even if X, will be true. Okay, so these two put together is what it makes it an inductive invariant. Okay, it's inductive as well as an invariant, because an invariant is a property which requires that for the program, that every execution starting from the entry point to that point at which Li is associated, that Li has to be true. Now, the third thing that is required in order to be able to use this loop invariant to prove properties upon exit of the loop is the third condition, that an inductive invariant is also said to be safe for a particular property, that P that you want to prove upon exit of the loop, if it is able to prove P on exit of the loop. That is, if a loop invariant is true at the head of the loop, and LC is false, the loop entry condition is false, then that is the situation when you exit the loop. Okay, you don't enter the loop. In that case, P should be true. Okay, so with these three, if you can propose a loop invariant that satisfies these three conditions: initiation condition, inductiveness condition, and the exit condition, that is sufficient for you to establish that if you start from whatever assumption in the program, that when you exit the loop, then the given post condition will is guaranteed to hold. The important thing is once you propose this loop invariant predicate, then you no longer need to unwind the loop. You can decompose your the proof of correctness of the program with the loop into 3 loop-free segments. Okay, one that checks, establishes the initiation, does the initiation check. That is, you start from the assumption and you execute the fragment of code that appears before the entry point to the loop. Then the loop entry condition holds. I'm sorry, the loop invariant holds good. The inductiveness check guarantees the inductiveness with respect to the body. And the exit check ensures that it is safe. All these 3 things are loop free. I mean, assuming that the body does not have any loop. Now, if the body, if it's nested loops, then what you will have to do is you will have to propose a loop invariant to cut every loop in the program, and then you can kind of do this proof bottom up, eliminating one loop at a time inside in a bottom up fashion, starting from the deepest nested loop to all the way to the top. Okay, and that is the real catch of this thing. Okay, so one way to handle this loop, we saw, you settle for an incomplete procedure, which is what is called bounded model checking. Another way to do is to have a complete way of doing that verification is to be proposing this loop invariant. Okay, so any questions? Okay. And that's one, this aspect of inductiveness of a particular predicate with respect to P and the safety. It is this thing, the iteration, the whole inference rule corresponding to this loop invariant with respect to the loop itself is described by this. Okay? Here P is the loop invariant. And if you can propose a loop invariant, and if that is inductive, then what it says is then upon exit, you know that P is true and not B is true. Now that is kind of this, something that you can guarantee on with respect. This may not be the strongest one. Anyway, so the P and not B will be true, which can then be used to prove any other post condition. So this is a way of stating that given a loop invariant that is inductive, which is what the assumption about here guarantees, then you can, this says that you can be sure of, it says that P and not B can be true upon exit, which can then be used to do this decomposition that I showed. It's just the initiation part is not part of this inference rule, but that is what you will have to do to prove this entire program. Okay, so that is the enunciation of that loop invariant principle in handling to handle the proof of a loop. Okay, so I'll take the example that I introduced to make a few very important observations that give you insight into what this loop invariants are all about. Okay, you have to pay special attention to these observations. Okay, because that provides you with some good insight. Okay. Yeah. So we already defined what a loop invariant is, that it has to be a loop, a predicate li, if it is inductive, a loop invariant has to be inductive. There are two things that you can observe for a loop, So if and only if it satisfies these two things. It includes every possible state that can actually occur at that location with which li is associated over all iterations. See, the emphasis here is on includes, okay? It certainly includes every possible state that can ever possibly occur at that point. For example, at this point, I'm proposing even if x is true. It is certainly the case that every value that the program can take at this point is even. Okay, of course, even if x includes lot more states than what is exactly what can exactly occur, right? Because this one, it is even, and it is also, and the only values that x can take at this point is certainly it is guaranteed to be even, and it is something less than or equal to 20, correct? So, I mean, whereas even if x includes lot more values, okay? So generally, what if it is inductive, with respect to if the predicate is inductive, certainly it will be true every time you go around the loop, okay? Starting with any state with that satisfies the predicate, but it may, for a particular program, it may also include states that are not reachable for this particular program. That is one that you have to notice. And it is closed, okay? That's closed because, if you start with something that is even, after execution of the body, then of course you will always be, you will continue to be in that set of even numbers. In that sense, this therefore, that predicate loop invariant is, in that sense, it is closed, for all execution of the body. Okay, so is that clear? Okay, so so those are the two properties that any loop invariant has. It has to be closed. That's why the inductiveness check guarantees that. And it is, for a particular program, it may include more than one. It's certainly guaranteed to include all the actual values that x may take, or in general, all the if there are more than other variables, then it can take. Now, for example, here it doesn't say anything. Even if x is indeed inductive, is inductive, and it's even inductive loop invariant, but doesn't say anything about I. Okay, so I, as far as this predicate is concerned, I can take any value. Okay, so in that sense, this is not the strongest thing that you can say that is inductive at this point. That leads me to the second observation. The same loop can have multiple valid inductive invariants. Okay, for example, even if x, you already see, it is an inductive invariant because it is inductive and it is also true. It satisfies the initiation condition. Similarly, I less than or equal to 10 is also an inductive invariant, right? Because the first time you get here, I is less than or equal to 10. And if I is less than or equal to 10, every time you go around the loop, I is I have to be careful here. Let me see. Is this inductive if I is less than or equal to 10? Yeah. If I, certainly if I is, yes, if I is less than or equal to 10. That's correct, because if I is equal to 10, you never enter the loop. Okay, So if I is less than or equal to 10, then if you ever enter the loop, then I will be less than or equal to 10. So I is less than or equal to 10 is also an inductive invariant. X is less than or equal to 20 is also an inductive invariant. All these are different possible inductive invariants for this particular loop. Do you agree, or you have any issues or doubts about this? Yeah. Any questions? Okay. Yeah. So is if if a predicate, a bunch of predicates are individually inductive invariants, then a conjunction of that is also inductive invariant. Are there any other things? So what is, then you can ask this question, what is the strongest inductive invariant, strongest thing that you can say about it? So I'm claiming this is the strongest inductive invariant. It has to capture all the possible values that the variables that are being modified in the loop can possibly take, and only those values. Okay, that a predicate that captures all the values and only those, exactly those values, it would be the strongest inductive invariant. And in this case, this is something that you can say, and this is the strongest thing. Each of the ones that I've shown above are certainly inductive invariants, but they're not the strongest one. Yeah. So whereas this one exactly captures I has to be less than or equal to 10, and X must be equal to 2 times I. Okay. So what is the weakest thing that you can say? That's kind of a silly question, because the true is always inductive. The set of all states is always inductive, is an inductive invariant, because I mean that's almost sometimes you're not saying much by with that inductive invariant, because if true includes every possible state. So if you start with every possible state, a predicate which includes every possible state, obviously it satisfies the initiation condition. Okay, because you start with anything, you always get into some state that is included in true. And if true is true at the beginning of a loop, then obviously it is inductive, because after you execute the body, you will obviously stay within this within that. And so this is the strongest thing that you can compute. This will precisely and exactly capture the effect of, all possible values that the variables can take inside the loop for all iterations. This particular thing. Yeah. Yes. And yeah. Now, but the question is, what inductive invariant is safe? I use the term adequate. How would you know which one to use and which one to propose? Okay, given a proposed inductive invariant, you can always check if it is inductive and if it satisfies the initiation condition. So the choice of a suitable inductive invariant, that it depends on what your post condition is like. So given a particular post condition that you want to prove, that is a property that you want to prove upon exit of the loop, then your inductive invariant has to be adequate, has to be strong enough such that it satisfies the safety property, that is the exit check property. Okay, so the kind of invariant that you propose, you will have to be somewhat clever. Okay, in proposing proposing that invariant. So I'll start with this. Suppose my exit condition, I mean the condition that I want to guarantee upon exit of the loop is I is equal to 1. What is adequate or safe enough inductive invariant that guarantees me that? Anyone? Attempt to guess? Now, this requires some amount of thinking, but once you get the hang of it, you will get it. But it is always challenging, even for a human being, let alone deriving it automatically, which is required, okay, to automate verification of loops, which is one of the most challenging things, and it also happens to be that's undecidable. Okay, so if you want to get I is equal to 10, I'm sorry, not 1. I think I have it as 10, no? Because I have a problem with I is equal to 10. See, notice this particular post condition is yes, okay, it's exactly the negation of the loop entry condition. So it is almost trivially satisfied. I claim that in this case you can use the weakest. Okay, remember that we saw that whatever that conjecture program, okay, that he saw. So it was almost kind of trivially true that if you exited the loop at all, this thing is satisfied, because the post condition is the negation of that thing. So you can get away with using the weakest loop invariant, okay, true whenever the post condition is just the negation of the loop entry condition. Otherwise, you have to. So for even fx, if even fx, you already saw that a loop invariant, even fx itself, ensure that even fx is true every time that you go down the loop, that is adequate, because when you terminate, even fx is true, and when you get out, things true. This is also somewhat of an easy case for you to guess. If this is the case in which your post condition, the predicate which denotes the post condition, is already inductive with respect to the loop, that it is already satisfies the closure property. That is, if you start in a state, in an arbitrary state in which x satisfies the predicate, x is even, then if you enter the thing and then you execute it, it continues to be true. So if your post condition passes the inductiveness check, then also it is fairly easy. So the first thing that I would do if I want to verify it completely is these things. If I first see if my exit condition is just the negation of the loop entry condition, then I'm almost trivially done in verifying the loop. If my post condition itself is inductive for that loop, then I can get away with proposing that itself. Of course, I'll have to check that it satisfies the initiation condition. Okay, so if this one itself is inductive, and then I'm only required to show that it is an invariant, okay, that it satisfies the first time. Then also it is fairly easy. But if it is something like, if your post condition is something like x is equal to 20, this is a case in which my post condition is not inductive. Okay, because if I start with x is equal to a state in which x is equal to 20, say a state in which x is equal to 20 makes no assumption about what the value of I is. So if I start with something with x is equal to 20 and I could be 1, then I enter, then I can end up entering the loop, and then X will get incremented to 22. And that's why this is not inductive. Is that clear? You have to, yeah, I want you to make sure that you understand the claim that I'm making, why X is equal to 20 is not inductive. I'll pick somebody, I don't know who all are there today. Let's see. Yeah, I'll go by in order. Anli, why is this not inductive?
So I could understand that I started with the value 0, and the post condition is that I would be equal to 10. But I'm also confused why X is not inductive.
Yeah, you have to go back to the inductiveness condition. Okay.
Okay.
Any condition or any predicate is inductive if it satisfies the following. If I start in any state in which X is equal to 20, okay?
Mm-hmm.
And if I enter the loop, then after executing the body, X must be equal to 20. So why is that not true here? Because this X is equal to 20 is not imposing any constraint on what I is. So a state which satisfies this predicate includes the state in which I is equal to 0, or I is equal to 9, I is equal to 8, as long as I is not equal to 10. Okay. So it's a matter of it can even include. So in that case, I do enter the loop, and what will happen after entering the loop and executing the body? X will become 22. So when I come back, it's no longer the case X is equal to 20. Therefore, it violates the inductiveness check. Okay, and that's why this itself is not inductive, although it's not inductive by itself. But but it is the case that as a matter of fact, it is not even. So this is a property that is true upon exit, but it is not inductive because it is not the case that X is equal to 20 every time you go around the loop. In order to prove this, what you need is something like this, like a loop invariant, which is much stronger than even of X. So if I propose X is equal to 2 times I.
You mean much weaker, right?
Yeah, much weaker. Yes. No, it is stronger. Okay. So even if X is weaker than X is equal to 2I. Okay. Because certainly it's weaker than X equal to 20. So I have to propose something which is weaker than, even if X doesn't cut it. Okay. I'll have to say X is equal to 2 times I need something like saying X is equal to 2 times I, okay, or yes, okay, in order to really ensure that upon exit that X is equal to 20. Okay, so you need much stronger than that. So the so the choice of your loop invariant, a safe and adequate loop inductive invariant that can get you that is adequate to do the proof, requires challenging, and the challenge lies when the property that you want to prove is not inductive or is not an inductive invariant. Then you will have to search for an appropriate thing. But one thing is for sure, that if you can somehow compute the strongest inductive invariant, okay, that will be adequate. That will be if the strongest inductive invariant, because it includes, and precisely, not only includes, but it includes precisely those values that the variable can never take the set of values over all iterations. That strongest inductive invariant will always give you a proof. Okay, will always be sufficient. But how do you compute the strongest inductive invariant? Okay, so that is the thing. So what you can be guaranteed is if you can somehow, compute the strongest inductive invariant, then it is, then you could be guaranteed that I can prove any post condition that I can pose. So such, getting the strongest inductive invariant is harder. Okay, I mean, is harder. Okay. Because of this, a failure, okay, given for a given proposed inductive invariant, failure to do a proof, by doing a proof, I mean checking the three conditions that I showed in the previous slide: initiation, inductiveness, and post. Okay, so maybe inductiveness and initiation condition are true in the sense that what you have proposed as Li is an inductive invariant, but still you may not be able to get the proof. But just because the exit check was not the exit check failed. But just because it failed, it doesn't mean that your program is buggy. It means that your proposed loop invariant is not strong enough. Okay, it's too weak. It's not strong enough to get you the proof. That means then what you need to do is to look for you need to strengthen it. You need to look for a stronger invariant. Like in this case, you needed x is equal to 2 times I. Okay. That's the thing. So as a side note, software verification, particularly model checking and abstract interpretation, the two things that we will cover, okay, in this course, can all be considered most as automatic procedures to search for the right kind of inductive invariant. They can all be at a certain level. At a certain level, at the core, they're all search procedures to search for the right, inductive invariant of the right strength to prove a particular problem. The traditional model checking methods, okay, always happen to compute the strongest inductive invariant. Okay, and doing that is, of course, that is decidable if your state space is finite, and this problem is undecidable if your state space is infinite. There may be fragments of logic in which for which it may be it is still decidable, but it is all and that's why even for finite state systems where it is decidable, the traditional model checking methods which relied on computing the strongest inductive invariant, they were all very expensive complexity wise. They were piece-based. Okay, so but now there are more fancy methods that look for not the strongest inductive invariant, but they look at the property and then try to use the property to be verified to guide your search for a safe enough, a strong enough inductive invariant to successfully verify. Okay? And one way or the other, different kinds of these methods can be considered, or all automatic methods for searching for this inductive proof. And that's why, at the crux of it, inductive invariant, it's very important for you to understand. And after today's lecture, I will be starting this abstract interpretation, a series of lectures to start covering the abstract interpretation methods, and they compute quite, a relatively weak inductive invariance, unlike traditional model checking methods, which always used to complete the strongest inductive invariant. That's why they were not as efficient. After covering abstract interpretation, I will then revisit model checking, complete model checking methods where, that's called some inductive model checking methods, which, compute better inductive invariance than abstract interpretation to, to be able to prove wider class of properties. Okay, so you can, this course from now on, all can be almost all our techniques will be. You will see that they are more, sophisticated methods to automatically compute inductive invariance to successfully complete the verification software attack. Okay, so I want to yes, and there. So what is the time? So it's 2:45. So let me just summarize this. Any questions here?
Sir, I have a question.
Yeah.
So, any technique that we use for finding the inductive invariant, is it possible that the inductive invariants that we find are incomplete and we get to a wrong conclusion?
Yeah, it may be. Rather than say incomplete, I would use the term inadequate or not strong enough. Okay. So yes. So what these? If you propose as a human being, as I said, if my if you propose an inductive invariant, suppose even x, and then your post properties want to prove x equal to 20, then your exit check will fail. Okay, if even if x, sorry, in this case, actually this is adequate, isn't it? No. If it is even, if x is even and I is equal to 10, there's no guarantee that x has to be 20. Therefore, yes, I would say it is not incomplete. See, the completeness is a very loaded term. Okay, it has a very specific technical meaning that I already described to you. Okay, a verification procedure is said to be complete if it is able to able to verify for any given property within a certain class. Okay, so that's how it is defined. So yes, what can if I rephrase your question as are they able to get all if they are able to always find an inductive invariant, that it may not be. Okay, they may not be. In that case, I will say that verification procedure that relies on searching for safe inductive invariants that are strong enough to prove a particular property. If it fails to find a strong enough inductive invariant, that it is incomplete. Yes. Okay. If that's what you meant, yes, I agree with you. Okay. But there are complete methods that are complete for properties. If your property is always a propositional property, okay, then there is a procedure which we will study later in the course called IC3 that is always guaranteed to terminate, and when it terminates, it will find an inductive invariant as long as the property, as long as your transition system is finite and the property that you want to prove is limited to being expressible. If it is expressible in propositional logic, okay, then there is a procedure, okay, where it is complete. So you see, if your system is finite, if your system is finite state in the sense that all states, all possible reachable states is finite. Okay, if your universe of states itself is finite, then all possible reachable state is obviously finite, and there are only finitely many inductive invariants that you can define on a domain which is finite. Okay, Therefore, you can enumerate, you can have a naive procedure which just simply enumerates all, if your domain has a cardinality of n, then your thing is 2 to the n, okay? All possible subsets, 2 to the 2 to the n, okay? That is the number of different possible invariants, inductive invariants that you never have. You can just enumerate the whole set of all inductive invariants and be done with it, okay? Obviously, that is not a good method, therefore it will be complete. So I'm kind of answering your question in a lot more elaborate way, that there are complete methods, and if it's incomplete, then it really means that for that particular thing, it is not able to complete an inductive, generate an inductive invariant. To that extent, what you said is meaningful and correct. Yeah.
Yes, sir.
Any questions? Okay. So here's a summary of core logic. Okay. This just puts all the inference rules together, including the iteration inference rules. So core logic, and here is core logic itself is sound and complete. Okay. It's sound in the sense, if I'm able to, using the inference rules, I'm able to deduce for a particular program that P, this is a valid or triple, using the inference rules, like the proof that I showed you as a tree, then see, usually soundness and completeness of any logic, for that matter, not let alone core logic, is defined with respect to an independent semantics of what it means for the program to be correct. Remember that we had already defined, using the structural operational semantics, a way to capture the meaning, which as set of all execution cases. Okay? And we will actually use that as the reference semantics to talk about soundness of core logic and completeness of core logic. That's how I'm going to define. And any automatic procedure that automates this logic or any other for software verification can then also be viewed, its soundness and completeness can also be expressed in a similar fashion. So that's how I'm defining. So if I'm able to deduce that a particular core triple is true using the inference rules, then for every given evaluation, then that, the interpretation, okay, that has to, for which P is true, then, if I start with any state in which satisfies P, then if I kind of use the structural operational semantics to execute this Q sigma, starting from the state if state, then if I executed the program Q in that state, which gives valuation for the various variables, and then if I end up successfully, I terminate with the tick state without any error, with a valuation of sigma prime. And that was very precisely and formally defined by our structural operational semantics. Then sigma prime should satisfy R. Okay, so that's what soundness means. If I prove something using the inference rules, then I should always that should be correct relative to the execution semantics that I prescribe. Completeness goes the other way around. Okay, that for every, if I know that if I start with any state that satisfies a predicate, I execute the program and end up in evaluation for that every evaluation that I get satisfies R, then I should be able to get a proof, okay, of it using the inference rules. Okay, so all these things can be, can be established in a formal sense, but I want you to just kind of understand conceptually what this soundness and completeness means. And the soundness, as I said, is guaranteed because you can check for yourself, okay, that each inference rule is sound, okay, by ensuring yourself that if you start with any valuation in which P is true, and if I execute as per the structural operational semantics that we define, then any evaluation that I get after executing the program will always be one that satisfies R. Okay, that's how you ensure that your inference rules are correct. Okay, so if any verification procedure that automates this, you can also attribute soundness and completeness, with respect to that. Now, this soundness and completeness, obviously, as you can see, application of these inference rules are almost mechanical, okay, because they are, deriving the thing. It was almost mechanical. They primarily involve substitution of expressions for variables. The trickiest part was these things, okay, where you had to prove certain obligations, okay, that you get at the end, okay. So in some sense, completeness of whole logic is relative to what kind of logic you allow for expressing my predicates, okay. If my predicates are restricted, say propositional logic, then so it's relative to this thing, as we already saw. Propositional logic is decidable. I can use a SAT solver to discharge this. Therefore, whole logic is complete and sound for propositional logic. Now, similarly, if for quantify free SMT logic with decidable theories, if I restrict myself to theories that are decidable, and then that's what I use to express my properties, the formula that define all these predicates, then it is also decidable. So the point I'm making is this completeness is relative to the logic that I allow for expressing my predicates. By restricting those, and since I'm relying on SMT, so obviously that logic has to be decidable, because eventually I should be able to discharge those properties. So it is relative to that, and as long as I stick to my verification procedure that is based on whole logic or inductive, model checking, or whatever methods, as long as the predicates and the formulas that I manipulate there are restricted to decidable fragment of SMT solvers, then those procedures are used. Those verification procedures are complete for properties, within that logic. Okay? So that's the point that I wanted to make. Okay. Okay, I still have about 10 minutes. So are there any questions? So what we saw here was, proof logic, and this is the end of a discussion. We only discussed about partial correctness and not about total correctness. Later on in the course, when we address the topic of termination, we will get to total correctness. Okay, and we kind of saw more than this. So we saw this connection to a bounded model checking, okay, through as a way of automating the forward proof, and that's what I get to in the next 10 minutes to just make a few observations about that thing. Or maybe I can even stop at this point. Okay, maybe I can take that next time. So I don't know. Do you have any? How do you guys feel? Are you sleepy, or you can take another 10 minutes? or you want to start afresh? Okay. So my
Will you
now,
be starting a new topic?
yeah.
Will you be starting a new topic now?
No, not new topic. It is just some implementation optimization notes about bounded model checking. So maybe it's better to do that, because that when you're some of the things that I've discussed about SSA are fresh in your mind. So I'll indulge you. Okay. Let's see what happened to that part. Get to this thing. That's what I wanted. So whether I'm able to complete it or not in 10 minutes, let's see. Slide. No, sorry. How do I get to full screen mode? Shit. In Windows, it's a peculiar application in which I can see. I think it's enter full screens. Well, this is the best I could get. I mean, I wanted to eliminate these. Play is the one. Yeah. See, you already saw earlier in our lecture how you could, when I introduced semantics. So there was the transition system semantics, and we even saw how you could come up with a transition system by introducing a program counter. Okay, recall that? Okay. So, if I add to the state a PC component, and then I can define a transition system which captures a single step of execution of the program in terms of the pre and post variables. Okay, the state space includes PC and values for the variables of the program variables X and C and T, and then you can define the transition system which captures the result of executing one step. Okay, in terms of the PC. This I described as kind of a global way of doing it. Now, if I want to do bounded model checking, then I can unwind the transition system. Okay, so then I can actually construct a formula. Okay, if I want to see if there is up to K unwindings of this transition system. Bounded model checking is all about finding, checking if that there are no bugs up to a certain depth of unwinding of your program. Okay. Now, if I capture the transition system in this fashion, then I can unwind the transition relation itself by constructing this formula. I start with an initial predicate. Okay, I'm sorry. Yeah, and IS0, and then and I will unwind the transition relation by actually instantiating the formula for the transition system K times, and then check that in every state from S0 to SK, that P is not of P. The property that I'm checking should not be violated. And then I can ship this formula. That is what I was doing, when we saw the SSA. But SSA was a particular way of capturing the semantics. Okay, and I claim that the SSA formalism to capture the set of all behaviors is better than this transition system. So I'm just comparing the transition system that you've already seen earlier with the SSA formalism that I introduced, which was motivated by the forward assignment rule, the SSA semantics itself. Now, the problem with this way of modeling and using the transition system is that firstly, you have introduced the PC, okay, which is kind of is a new state, okay, and that is adds to the possible values in the state. But more importantly, most of the formula is never used in your unwinding, because usually the program has a structure, okay, which is actually the CFG, the control flow graph, whereas that information is kind of lost in this way of defining the TC, because this says, oh, the transition relation will, in each instance of it, when I instantiate it k times here, we'll have a lot of parts, where the PC, the transition of PC is never ever used, and therefore this formula has a lot of parts that are never going to be true. So that's what is indicated. If your CFG is something like this, then if you use the global transition system, you would not. Okay, for example, from L1, you can never have a path which goes continuously stays at L1, because from L1 you have to either move to L4 or L2. Once you reach L4, it can never be the case that you can continue to stay at L4. Whereas the unwinding based on the global transition relation that I showed earlier will have these things. Therefore, the formula that the K unwinding, which represents K depth unwinding of your program, will be huge, because it contains unnecessary parts. I mean, that are never used, and therefore the idea is to use the to use the CFG, okay, something where you can use the CFG to get to only those parts, okay, that the CFG generates, because the parts that the CFG generates are really, in some sense, the parts that are ever possible. Okay, so for example, from L1 you can only get to either L2 or L4. From L2 you can get to only L3. From L3, of course, you can get to either L2 or L4. So if you used the CFG before the unwinding, if you did the unwinding on the CFG, then you have then you'll be generating only, and then generate your formula that you need to generate the formula for every path. Then your formulas will be lot slimmer, okay, lot leaner, and that is the idea when you're dealing with software. If you're dealing with hardware, the unwinding that I showed before in terms of the transition system is fine, because hardwares don't have a CFG. But for software, any kind of unwinding is better with if you used that works over the paths, especially when you unroll the things. And that is what CBMC does. Okay, one way to automate this bounded model checking, which relies on unwinding, is to unwind the CFG, and then for every path individually, you can generate something like an SSA. Okay, that was the kind of idea. So then, for every path, because it's a straight line program. Every path represents a possible straight line slice of your original program. Then you can use the SSA formalism to generate the all possible intermediate values. Okay, but the disadvantage is of enumerating all the paths is that there are exponential number of paths in here, right? Because if you enumerate all the paths, then if you have conditionals inside inside your body of the loop, then the enumeration of all the paths itself you'll have exponentially large number of paths, and that's why where you had this notion of the SSA came in kind of handy. But yeah, and I will get to that. See, this merge trick that you used by introducing extra variables will get around having to unwind and enumerate the paths. But I will get to that. But before that, I will, and that's what SSA is providing. Nonetheless, okay. So remember the last class I said that bounded model checking involves unwinding the loops up to a certain depth. Okay, and then to check if unwinding is adequate, then the way CBMC does this, after you unwind to up to a certain K depth, it adds automatically an assertion of this kind. At the end of this unwinding, it automatically inserts this assertion. It says, check if negation of the condition is valid, okay, is always true. If it is not, if it is true, then you know that that you have done enough unwinding. If this is not true, that means that there still is some values, states for which you can enter the loop. So there are more unwindings that are possible. So if this, as long as this condition is violated, then it means that your unwinding is not adequate. Okay, and this is what CBMC uses to do that. So let me get back to this thing. So here, how does using an SSA ensures that you have? So I only have one more slide, and that's what was given by that I illustrated. Okay. Here. Okay. So remember this program. So if such a if then else was inside, say, a while loop, and bounded model checking, if you use just brutal unwinding and you generated one path for every unwinding, then you will have, if there are n iterations, and since each iteration you will have to explore two different paths depending upon x is greater than y and so on. So for n unwindings, the number of paths, individual paths, will blow up. Okay, but look at how we are avoiding this merge by introducing these merge variables and these conditional expressions, by embedding that effect of that split inside your SSA, and that is where the whole rule corresponding to forward, whole rule corresponding to if then else comes in handy. Now if I generate for the body such in terms of the merge inference rule, then I no longer, then this is just the unwinding, or will not exactly have that exponential blow up. That is the subtle point that I wanted to convey. Okay, and
could you make that point again?
Yeah. So there are two ways of how you could implement bounded model checking, okay, on software. One is you unwind, you enumerate all the paths, okay, which will be straight line programs, okay, and then I use the convert them, generate SSA for each of those paths. Okay.
And how does this prevent?
Yeah, the way it prevents is after every in the body of the loop, you construct the SSA in this fashion. Okay, SSA for the body. So
Okay.
and then what you do is kind of a linear unwinding of that. You will just will produce as many instances of this SSA formula, okay, in when you unwind, okay. So I won't be I mean the simplest thing is to consider this program. Yeah, consider this program here. This is a case, okay? One way to handle this is generate one, path, okay? For every, there'll be, 3 cases and you have 3 different paths, okay? Then you have completely straight line branchless paths, and then you can generate an SSA for that. Okay, there'll be 4 different SSAs. That is okay as long as you have straight line programs with branches. Okay, but if this is embedded inside a loop, then if you enumerate each of those paths, then you will have exponentially large number of paths. Instead, what I'm saying is I will generate a single formula that merges all these paths, these if-then else's within that, and that's what I kind of did by using these merge variables. Okay, and then when I unwind using this thing, before I unwind, what I'm plugging in the body, I'm not unwinding all the if-then else's parts inside the body. Okay, so inside the body, I'm merging all the if-then else's. Yeah, before I unwind the loops. Okay, and therefore, so in that sense, I'm preventing enumeration of all parts. Okay, of all parts, which are for each iteration there'll be multiple parts. That blow up I'm avoiding. Yeah.
But I don't understand. So I understand the number of decisions are being taken less number of times now. But
no, I'm merging the decisions. Think about it. So
but you're not really merging, right? There's still an if-then else, which is just
no, but it's a single expression, single expression. Okay.
But to solve it, we still need to.
And what I'm doing is all these things will be repeated on every path. Okay.
Yeah,
so,
I'm saying that to decide the values of, or to decide the satisfiability, we still need to enumerate all those parts.
Yeah. The question is, okay, I think we can, I don't want to take too much time. You're already going, so we can take this thing. Think about this, okay? I have to restate what I've just now stated, okay? And you'll have to think about it, okay? And the way is, you can, how many, if I did not merge this, okay? When I merged this, I got a single formula, okay? Which had this equality, okay? There was a single formula, right? Now, if I did not do this, and if I had a separate thing for each, then I could, this is a single formula that represents the entire body. Now, if the enumeration, if I did, I will take if x is equal to y, then this, and for that x is equal to y, then I will, and if I multiply that, okay, strictly I can enumerate in the unwinding, create as many distinct paths for each of the conditionals. Okay, each of the conditions. So then I'll be repeating these things. Okay, so in each for each iteration I'll be enumerating, and that is what I'm avoiding by merging these things.
I will think about it.
Yeah, think about it, and if you, we will start with this clarification of of this thing. So I'm claiming that enumerating all the paths, and generating the formula for each path versus having a single formula which will have an if then else inside that, and before I unwind, okay, then there is a difference. Okay, is what I'm saying. So so try your this thing of that I claim there'll be two to the n different formulas, whereas here there'll be a single, somewhat fatter formula which is linear in the number of iterations. That's all I'm saying. Yeah, and work it out. Okay, have in this if then else inside a loop, and then enumerate all branchless straight line paths. Okay, you have to check 2 to the n formulas, whereas here you will have to check for each iteration a formula that is linear in the size of the formula that you require for a body. Okay, that's the distinction that I'm making, and you work it out, and I will show you where the saving is. Yeah. So yeah, I've gone way beyond everything, and sorry, and I will stop here and mark your questions, and then we will continue next time. So end.